Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. We will look into again two things we will do this time around. We will go into quantum circuits and quantum gate operations. However, a part of it has already been done in our previous lecture. This is more of a recapitulation and consolidating your understanding as far as quantum computing, especially in the area of quantum gates and quantum circuits are concerned. Now, just to start from where we left in our previous lecture, for example, if there are 100 to 300 logical qubits available, then current quantum error correction techniques will require thousands of physical qubits, right? And which means that if there are say 100 to 300 qubits, there are a large number of states available, right? 2 to the power 300 states available. And these states, if there are error corrections required for all the states, you can very well understand the number of physical qubits you require to do it. Now, forming this physical qubit and controlling them from an external source is a big overhead which happens. And primarily this error correction will come because of decoherence, a correction of decoherence. There will be gate errors and there will be also crosstalks within the qubit. Now, overhead is obviously a major significant in superconducting in trapped iron platforms. For superconducting and trapped iron platforms, the overhead is especially significant, right? They are pretty large in numbers, right? There are certain emerging solutions which are coming from technology point of view, and these are referred to as CAT qubits, which offer actually an intrinsic error resilience, which means that you do not have to do an error correction internally. It offers you by itself a large amount of error resilience circuits, and therefore these may significantly reduce the number of physical qubits required per logical qubit, right? And that is the sort of the domain in which a large amount of work is going on across the world. Now, let us look to the quantum circuits, right? Now, quantum circuits are basically a mathematical model. So, it is unlike our circuits or the circuits which we study conventional in digital electronics or analog, where there are physical wires. These are basically models which represent the flow of information. At the end of the day, any quantum computing system is primarily meant to process and flow the information so that you get the minimum error available to you, and the fidelity should be very high. So, what does quantum circuit do is basically it is a mathematical model, and that represents the flow of quantum information from physically from point A to point B, right. As I discussed with you, it consists of qubits, quantum gates, which we have already studied X, Y, Z. We will come to that later on as well. And there are certain protocols of measurement, right. How do you measure the state of a qubit? And therefore, there are certain measurements, not only how, by what method you use it. For example, do you use optical or do you use high frequency microwave? What is the center frequency and bandwidth of the microwave for the best resolution of the qubits, and so on and so forth. However, as I told you, quantum circuits follow the principles of quantum mechanics. They do not follow classical mechanics, they follow quantum mechanics, which means that there will be always a amount of uncertainty there. Now, when you pass these qubits through a gate and when the qubits are measured, the outcome is always a definite outcome. So, I will have a qubit 0 or a 1, but output will be either 0 or a 1. But once it is in its own state, qubit state, it is either superposition of both 0 and 1, right. As you can see on the left, on the right hand side, the figure which is given. So, I have these are the qubits which are there, and when they pass through the gate, this is the measurement sort of doing, and this is the measurement I am doing it, and after measuring, I am putting it all on this control bus. There are 3 control buses which is taking it. Now, the output of this control bus will be always a classical outcome, which means that either I can have a 0 or 1. So, when you measure something, the outcome will always be classical, right. But when you do not measure something, it will be always in a state of quantum sort of decoherence, or a quantum state where it is a superposition of 2 states being shown to you. So, this is a gate, and by applying a gate, I am doing a measurement from this angle, and the output is put as the point number 2 in the output line. Now, as I discussed with you, quantum gates generally apply operations to qubit, changing the quantum states. We just not did that. And the strength of a quantum circuit depends upon 2 factors, and one is superposition, another is entanglement. Superposition basically means the qubit exists in multiple states simultaneously with weighted mean for individual states, right, where the qubits exhibit in multiple states simultaneously. What is entanglement? Here the qubits are related in such a way that classical qubits cannot be. So, action at a distance sort of movement, that if you are able to extract the state of one qubit, you can be assured of the state of another qubit, which is in no way physical contact with the first one. And so these properties of superposition and entanglement allows me to have multiple states available, not only multiple states available, but I can also control a state physically which is too far away without even sort of an action at a distance, and therefore classical computation fails in those domains where the quantum computing comes into picture. And that enables the basic quantum circuits to solve these problem statements to a larger extent. Okay. Now, what are the key components of quantum circuits? Qubits are, as I told you, these are again the basics. Again, the qubits are basic quantum equivalent of classical bits, and therefore, as I discussed with you, qubits can exist in multiple states due to superposition, and because of that you can have multiple number of states from a single qubit, and therefore the number of information carried by these qubits are relatively large. Quantum gates, these gates are operators that manipulate qubits. Some common gates are basically, as I discussed with you, Hadamard, Pauli and C0. Within the Pauli there are 3 gates X, Y, Z. Let us look at Hadamard. Superposition is created by a qubit by putting a qubit in equal probability of both 0 and 1. That is a Hadamard gate. So, we have equal probability of having a 0 and 1. So, 0.5 and 0.5 happens the probability of 0 and 1. Let us look at the Pauli gate. Pauli gate are referred to as X, Y, Z gates, and what you do is, when I had taken to you, there is a block sphere available, right, and you rotate the block sphere along its axis, either in a clockwise or a anti-clockwise manner with a theta of pi by 2, and when you do that you convert one pure state to a superposition state and so on and so forth. So, Pauli gate helps me to do that transformation from along the block sphere. Now, C0 gate actually creates entanglement by flipping the states of the one qubit based on the state of the other qubit. So, C0 gate, as just like an inverter, flips the qubit in its original state to its final state. There is another gate which you might not have heard, is basically a Toffoli gate, and these are used for, I will not discuss too much in detail, but these are used for reversible computing and quantum error corrections, right. Swap gates are responsible for swapping the states of 2 qubits. So, if there is 2 qubits available in state 0 and 1, and if you put the swap gate, the 0 will contain 1 and the 1 will contain 0. So, there is a swapping of the bits. And measurement, as I discussed with you, that basically collapses the states of the qubit into definite states. So, moves from quantum to exactly classical phenomena, and the measurement results are critical for interpreting the quantum computation. Whereas quantum states are probabilistic in nature, measured states are always definite depending upon the measurement techniques which has been used. So, let us look at how the quantum circuits work step by step. So, initially we do an initialization, and let us suppose I have a starting state and I assume that the starting state is a 0 state. So, this is an option of state actually, right, in a state, and this prepare qubits for computation purposes. Then you apply gate to it, right. So, can be applied in a specific order, and they create therefore the superposition and entanglement pairs over a region, and this enables you to perform a complex quantum operation. So, let us suppose you have a block sphere. In a block sphere you are told to design, or you are told to say that the vector moves by pi by 2 to the clockwise direction, then you know which gate to apply, or pi by 2 to the anti-clockwise direction, then you by which direction. When the block sphere moves, the superposition quantum states, the weights go on changing, and the weights go on changing, they carry fresh information. So, this sort of entanglement and superposition is possible when you do a quantum gate application. As I discussed with you, superposition works with multiple states, and qubits works with when it affects changing one affects the other is referred to as an entanglement. Again, then qubits are measured and then, so this is a classical measurement, and the state collapse to either 0 and 1, and the output gives the result of the computation, and the output gives you a classical result. A fixed value either 0 and 1 is obtained to you. What are the advantage of parallelism is that speed up. Basic advantage of parallelism is speeding up, which means that you are able to speed up the circuit at a much faster pace when you do a parallelism, right. Okay. Just a small numerical problem. I say that a single qubit is in the state shown here. What is the probability of measuring the qubit in states this thing. To find the probability, we square the coefficient of 1 and then we find out this to be as root of 0.7 whole square, which is 0.7, which is 70%, which means that 70% of its probability of finding 1 in the mixed state of 0.3 and 0.7, right. So, the mixed state of 0.3 and 0.7, we get that to be the probability of the state. Okay. So, this gives you a brief idea about how to find the probability. So, similarly state 0 will have a probability of 30% and so on and so forth. Now, you can change. So, when you apply gate, these coefficients starts to change, right, and therefore, the probability of 1 and 0 varies as you change the vector from its original position of 0. So, if the original position is 0, means this will be the original position, you will have 1 here, and then as you go on changing it, this goes on decreasing and you will go on adding the 1 state, right, and this 1 state goes on adding, you gives you a fresh value of the psi value, right, the state of the psi. So, this gives you a qubit state probability understanding. Now, let us come to quantum circuits and let us apply maybe an Hadamard gate and let us apply X gate, Y gate and see how it works out. So, I have 4 qubits Q0, Q1, Q2 and Q3, there are 4 qubits. So, I need to initialize this whole circuit such that all are initially 0 state. So, you see this psi 0 is basically my 0 0 0 0 state, right, and therefore, all the 4 qubits are initially at 0 state. This is known as initialization of the state, and this is important because if you do not initialize it, it is fully random, you will not be able to predict what will be the final state as such in a quantum circuit. So, when you join these two, it basically means Q1 and Q0 have the same probability. I apply a Hadamard gate here, right, I apply a swap gate here also. Then I have got X gate here and Y gate here, and then what happens is that I am saying that this Q1 is applied to a Y gate and this converts Q1 into Q2 and so on and so forth. These are the states which you are feeling. So, this is state number 1, this is state number 2 and this is state number 3, and that is represented by psi 1 state, psi 2 state and psi 3 state. Now, this is a methodology of showing you how information is being processed in a quantum circuit, right. So, this is a Hadamard gate, this is a swap gate. Hadamard gate will give you a change in the superposition state and swap gate will swap 1 to 0 and 0 to 1. And therefore, if the Q0 initial value was 0 and if this value passes through a swap gate, this will be converted to a 1, right. And similarly, if it was initially 1, it will pass through a swap gate, it will go to a 0. And the state change takes place at psi 1, psi 2 and psi 3. Now, let us apply Hadamard gate on Q0. Q0 was initially equals to 0. So, what I say that h of 0 equals to 1 by root 2, 1 by root 2 because 1, so it is basically 1 square plus 1 square root over, a square plus b square root over, and that comes out to be root 2 here. So, the total state becomes 1 by root 2, 0 0 0 is the initial state and then you finally get 1 0 0 as the final state. So, 0 0, when you apply the Hadamard gate, you get this state and this state. So, basically the matrix multiplication takes place and you get 1 0 0 here. Now, after that apply C0 gate with Q0 as control and Q3 as target, right. You apply Q0 gate. So, C0 flips the target qubit if the control is 1. If the control is 1, we will flip it. So, what we do, we apply C0 with Q0 as the control and Q3 as the target. So, this is my control and this is my target, right. We apply this C0 gate and this is the C0 gate which you apply, and C0 gate flips the target qubit if the control is equals to 1, right. So, what you do is 1 by root 2, again the initial is 0 0 0, the initial Q0 value. Now, it becomes 1 0 0 1 because there is a flipping of the 0th state, the last state, because it sees a 1 and therefore, it flips to 0 0 1 in that sense. Now, we apply control CZ state or control Z state on Q0 and Q1, and which means that since Q1 equals to 0 initially in both the components, the CZ gate has no effect, and therefore, it exactly remains, psi 3 remains like this thing. Psi 3 is what one? I can show it to psi 3 is this one state here. So, let me show you what is psi 1. Psi 1 is this one which is at this particular point, right. Then psi 2 is this one which is at this particular point. So, what I have done, I have applied a Hadamard gate, right. I have applied a Hadamard gate, I get this, then I applied a C0 state, right, and I get this. Then I apply control Z on Q0 Q1, I get this, right, and then we apply an X gate on Q3, and the fourth. So what happens in the X gate and Q3 is X gate actually flips my data, and therefore my psi 4 becomes equals to 1 by root 2 into 0 0 1, 0 flips to 1 here, and I get 1 0 0 1. So 1 0 0 1 is coming from where? 1 0 0 1 is coming from this one, right? And so 1 0, so this is 1 0 0 1. When this 1 flips to 0 and 0 flips to 1, which I have already discussed, and 1 flips to 0 and 0 flips to 1, and we get this as the fourth qubit in both the states, right. Now what we do, we apply S gate on Q0 and Y gate on Q2. So we apply S gate on Q0 and Y gate on Q2. As I discussed with you, swap S gate adds a phase of I to the state of Q0, and therefore Y of 0 becomes I of 1, right. I of 1 because the Q1 was carrying 1 here. So if you apply this concept on 0 0 0 1, Q0 equals to 0, there will be no phase from S, but if Q2 equals to 0, then Y becomes complex of 1, which means a complex of 0 0 1 1. Similarly, for 1 0 0 0 means 1 0 0 0 state, if Q0 equals to 1, then S adds a phase I, whereas when Q2 equals to 0, Y becomes equals to minus 1 0 0, and you get the final value as phi is equals to 6. So the whole idea is, by applying these swap gates, Y gate, Y poly, X poly, Hadamard and C naught, control Z, we are able to change the state. Changing the state effectively means that the state itself and its corresponding weight we are not concerned at this stage, but in most of the cases the value of the bits, the qubits will actually change, the state will actually change, right, and that gives you a good idea. So with this, let me recapitulate what we did till now. We looked into the basic sort of workflow in the quantum circuits, right. We looked into the application of various gates onto the quantum circuit and how does it influence the states of the circuit. We also looked into the fact that by application of multiple gates, different types of gates on various qubit values, I will be able to extract the final state of the qubit at certain point of time, right. And so we have learned one thing, that by application of these gates you can actually manipulate the state of the qubit, and you can therefore have added information available to you as far as quantum computing is concerned. So I hope you enjoyed this lecture. Till we meet next time, goodbye.